Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to talk about Stan, which is our probabilistic programming language. So this is a slightly different approach to a project than what we've seen before. I'm Bob Carpenter, one of the core developers for Stan. We've got a fairly big core development group, which is listed up here. So we're doing these in two parts. So what I'm going to start with is telling you what Stan looks like now, and we're currently in the 2.4 version. We've been released for a couple years now. So what is Stan from a high level? It's an imperative probabilistic programming language. So there are other kinds of probabilistic programming languages out there, like Bugs, which was sort of the previous state of the art, I think, before Stan, which is declarative. And then there's a language called Church, which is functional, which is sort of looking forward a bit, but isn't really particularly practical for real problems yet. And there's an object-oriented alternative that I just learned about but don't know much about. So what does a Stan program do? Well, it declares variables and codes a log posterior, basically, or a penalized likelihood if you prefer to think in frequentist terms. And then what does Stan inference do on top of a program? Well, it does sampling for full Bayesian inference, or it does optimization and curvature estimates for maximum likelihood estimation and uncertainty. So let me give you a simple example to sort of ground what we're doing here of what Stan looks like. This is a very, very simple example just for estimating a Bernoulli probability. Right? So we have a data declaration that declares the number of instances. Each instance of data is Boolean, so it has a lower bound of 0 and an upper bound of 1. We declare that as an array y. There's a single parameter theta, which is bounded to be between 0 and 1, and the bounds are important here. And then we have a model that says y is distributed according to the Bernoulli distribution conditioned on theta. So the assumption in this model is that the prior on theta is going to be uniform. Anything that's declared as a parameter and doesn't have a declaration is going to get a uniform prior, but you could add priors in as well. And the expression for y here is vectorized. It automatically loops over all the versions and adds it. So in general, the goal in Stan is a user has a particular kind of probabilistic model they want to explore, or a space of models where they want to explore. So rather than wanting to take some kind of off-the-shelf learning method and apply it to my particular data, our users are typically fairly sophisticated statisticians, mostly grad students, faculty members, research people at companies, who want to build fairly involved statistical models, not something like this. And they often don't know the model that they want to build, so they often want to explore the space of models as part of doing this. So our emphasis is mainly on efficiency, but efficiency constrained such that we need to give users the flexibility to express the kind of models they want. So what happens? Well, I'm showing you now input and output using our R-Stan interface. So this is the interface to Stan through the R programming language. So we set a number of observations to 5. We set our observations, which are 2 positive and 3 negatives. And then we call a fit by calling the Stan function. Bernoulli.stan was the name of our model. We provide the data, which is n and y, using R's funky environment stuff. And then we do a print. Here's what the print looks like on the output. We print the mean of theta. We print the standard error. This is the MCMC standard error in our estimation of the mean. Then the posterior standard deviation, some intervals. The number of effective samples, which is very important. This is the thing that goes in the denominator, square root of n, when you're computing the MCMC standard error. And then convergence metrics. Then we can do things like extract the fitted data and plot a histogram of theta. So this looks like the posterior plot for theta for the fit, given this data and running through this model. Oh, how long do I have, by the way?
20 more minutes.
20 more minutes?
Including questions.
Okay. Stan is open source, so the core of it's written in C++, and we have a command line interface. Those both have the new BSD license. The PyStan and RStan interfaces are GPL version 3, and then we have dependencies on the Eigen C++ library for matrix operations and Boost for a lot of template metaprogramming, parsing, things like that. And we use Google Test for unit testing. So we're hosted publicly on GitHub. We've got issue tracking and so forth run through GitHub. We also run everything through pull requests and code review with continuous integration hooks into our Jenkins server. And we also have public mailing lists separated for the developers and for the users. So the platforms that we run on are pretty much all of Linux, Mac OS, Windows. We need a fairly recent C++ compiler, meaning something written in the last 5 or 6 years, not something that's like 20 years old. The C++ API is portable and C++ 2003 compliant right now. And then we have interfaces for the command line, for R, for Python. These are ones that are developed by the core developers. We also have a couple user-contributed interfaces for MATLAB and Julia. Who's using Stan right now? Well, as I hinted at earlier, it's mostly statisticians. We have 800 some people on our mailing list. We're getting like 10 or 20 messages a day, so it's kind of overwhelming us. It's pretty much across all the physical, biomedical, and social sciences, plus applications in engineering. We just got an education grant from the Department of Education to do education models for tests and teacher performance, and also for marketing. So we've got a list of, these are things that we know people have written and published papers about using Stan. So there's a lot of other, we've got thousands of users out there. This is just what published papers have been. We have a long user's guide describing the programming language itself, and then for each interface, installation, getting started guides. Then we have a ton of examples out there. Most of the people we're targeting learn how to do this stuff by looking at examples of models like theirs. I'm an ecologist. I want to build a population model for ducks for 50 years in a particular wetland where I have data. Well, I usually don't want to figure out how to program that from scratch. I want to go look at somebody else's implementation of the Cormac-Jolly Serber model or whatever it is for doing this kind of thing. So we've got tons of examples. We've got all the bugs and jags examples. We've got all the examples from Gelman and Hill's regression books. I would highly recommend this new book by Eric Jan Wagenmakers and Lee called Bayesian Cognitive Modeling. One of their students has ported all of their code to Stan. This is a really nice introduction to Bayesian modeling that's not super heavy on the math side. There's a couple books in progress whose authors have contacted us because they're going to be including Stan, and we have a ton of user-contributed examples in our groups and our mailing lists. For scaling and evaluation, which is important to us, I really want to separate 3 kinds of scaling here that people want to talk about. One is sort of you fix your model and you just throw more data at it. That's easy scaling, right? If you're a statistician, getting more data just makes your life easier. At worst, you can subsample it. More parameters are a little tricky, right? Typically, when the number of examples grow, we're doing some NLP classification problem, the number of parameters grow with it. That's still fairly simple. What we're targeting is more complex models. That is, you want to throw a multi-level model on. You want to throw some kind of complex prior on. You want to take your LDA model, instead of saying a Dirichlet prior, I want to do some kind of multivariate logistic normal prior on it. That's the kind of thing that we're really targeting, is scaling up in terms of more complex models. Gaussian processes, for instance, with various kinds of covariance matrix estimate, all kinds of time series models that we're building. Well, I should say our users are building. We're not really in the model building business ourselves. So the metrics that we care about, since we're mainly doing MC sampling and doing optimization, is time to convergence, the mixing that we get after we converge, the amount of memory usage. And what we found is we have anywhere from 0 to infinitely many orders of magnitude improvement on the competition doing this. And there are some problems, there's 0, it actually goes to a little less than 0 in some cases. There are some conjugate models in Gibbs are really easy to fit with Gibbs samplers. As soon as you get to any kind of model complexity, you start seeing benefits to using Stan over any of the competition. And the reason we really developed Stan is we had a bunch of hierarchical regression models that we couldn't fit with anybody's software, right? So the reason that Andrew hired me and Matt Hoffman originally was to start building something that could fit these hierarchical models that no other software could fit. So that's where the infinity comes from, is there's lots of problems that our software can fit that nobody else's can. So when there's the more complex your model is, the more improvement you're going to see with our programming language. The way the models are set up is there's a data declaration. Everything's strongly typed here. So there's a data declaration that declares the data. These get executed in terms of reading once from a data source, validating the constraint. Then there's declarations for the parameters. Those declare the parameter sizes and, importantly, the constraints on the parameters, because every execution of the log probability, we do a mapping from the parameters to an unconstrained set of parameters. Though actually it's the other way around. We're doing our sampling on an unconstrained space and our optimization on an unconstrained space. So we apply an inverse transform from that back to the constrained space where we evaluate our model and automatically apply the Jacobian. Applying the Jacobian is optional if you're doing optimization, because maximum likelihood, as you may know, depends on the scale, right? Unlike expectations in a Bayesian model, maximum likelihood estimates aren't well defined until you pin down the scale at which you're doing them. If you change the scale that you're operating on, then the maximum likelihood estimates are going to change. Right? Uniform on the log scale is very different than uniform on a linear scale, for instance. The Jacobian will adjust for that, but we don't always apply that. And the model defines the log probability for the model, and that's something that gets estimated gets executed every time. We also allow blocks to transform data. So often you want to once take your data, transform it into some slightly different format. We allow transformed parameters, which transform the parameters, and again, you can optionally apply Jacobians there if you want. And then we have generated quantities for doing things like posterior prediction, event probability estimation, decision making, and these get executed once per iteration. We just added a functionality which I'm very happy with, because I'm mainly the person who deals with the low-level programming language issues. We have other people who specialize more in the optimization, other people who specialize more in the sampling, but I'm mainly the language person. So we just added an ability for users to define their own functions within our language, which may seem relatively simple, but it's very complicated with all the automatic differentiation that we do. Right? We have a bunch of different built-in variable and expression types. So there's primitives, integers and reals, there's matrices, and we, like MATLAB, but unlike something like R, differentiate vectors and row vectors. This is important for type inference. If you multiply a row vector by a vector, you get a scalar. You don't want to get another matrix out. You don't want to get some big overloaded object out for efficiency. We allow bounds to be declared, lower and upper bounds on our matrices. And we also have constrained vector types, simplexes, things that sum up to 1, non-negative things that sum to 1, ordered vectors. So if we want to do ordinal logistic modeling, right, we have some kind of ordered thing, we're getting data where people are ordering it. We typically want to do a logistic regression, and then there's cut points that decide where the order falls. We have constrained matrices. You can declare covariance matrices or correlation matrices, which is useful if you're building hierarchical models. You often have a couple, say, we're doing drug trial data. We have the reaction of a patient to a particular drug. There's a couple features of their reaction that vary by patient, right? But there's covariance among the way those features of the drug reaction vary by patient. So we can model that kind of thing using these kinds of constrained matrices. We have the basic set of arithmetic and matrix operators, logical operators, and then we have a very extensive library of built-in mathematical functions. This includes all the built-in C++ functions, including all the libraries that have become part of the standard. But we also have an extensive library of statistical functions, things like softmax and things that you need for normalization constants like log gamma functions, Bessel functions of the first and second kind, which you need to normalize some spatial statistical models. And then we have efficient and arithmetically stable compound functions, which the Theano team was mentioning earlier. We don't, unfortunately, do this automatically, but we do have things like log 1 plus x, so we can evaluate that efficiently. Things like log sum of exponential shows up when you're coding up mixture models, for instance, inside of Stan. Right? Then we have a bunch of built-in matrix functions, including basic type inference, which I mentioned earlier, all the basic element-wise arithmetic. This is very much modeled after MATLAB. So if you're familiar with MATLAB, it's pretty much the same sort of syntax there. We have the basic decomposition, slicing and broadcasting functions, reductions like sums and norms, things that take matrices or vectors and return scalars. compound operations, like for instance, very often if you're dealing with elliptical distributions, you need quadratic form, something that's going to multiply a vector transform times the matrix times the vector. We want to be able to do that efficiently with respect to the automatic differentiation that we use. And we need specialization. So we have special operations that apply to positive definite matrices like you find in covariance matrices, triangular matrices like you find in Cholesky factors. All of this stuff lets you efficiently implement inside of a STAN program multivariate models, right, which is one of our key focuses. One of the things you couldn't do easily with existing technology, right, for instance, in bugs and JAGs, you can only do conjugate multivariate models, whereas we want to have much more flexible conjugate models, non-conjugate models for this. So, for instance, we have a distribution library that pretty much has all the distributions most people have heard of and a lot that I hadn't heard of till users asked for them and we implemented them. They have the usual operations with them. We also provide alternative parameterizations, which can be a lot more efficient. So we have like a Cholesky factor parameterized normal distribution. We're very excited about a new multivariate correlation matrix density. This allows you to control, we typically use it as a prior on matrices rather than something like a Wishart or an inverse Wishart. And the degree of freedom parameter controls shrinkage to a unit matrix, which is a more natural way of thinking about a prior for a covariance matrix, to think of an independently constraining the correlation matrix with some shrinkage toward a unit and then independent scaling of the scale factors. So we're very excited about that and have a fairly efficient implementation of that. The language itself is made up of a bunch of statements. We have sampling statements which increment the underlying log probability in a way that's built in, or you can do it directly with expressions yourself. We have assignments, loops, conditionals, blocks, and then we have printing and exception statements. Well, I should say we will have exception statements at least in our next release. I think it's Q. I don't think it's in 2.4. I think it's going to come out in 2.5, but I think it's already passed testing and is all queued up and merged. So the two kinds of inference that we do for full Bayesian inference, where we want to do all of our inference by keeping all of our posterior uncertainty and integrating through any expectation we calculate, we're doing that with Markov chain Monte Carlo methods, and in particular we're using an adaptive form of Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is really nice in that it uses gradient information. Instead of doing a random walk, it actually walks around the posterior in a way that's sensitive to the contour, the curvature of the posterior. There's a lot of problems that we needed to overcome with this. I should say Matt Hoffman needed to overcome with this. One was adaptation during warm-up. So we basically use a dual averaging algorithm to adapt our step size and to adapt a mass matrix. So basically the Hamiltonian Monte Carlo is treating the parameter value as a particle. It's treating the negative log posterior as a potential energy field, and it's imparting a random momentum term. And then we're actually solving the differential equation using the Hamiltonian mechanics to move from one side of the distribution to the other side of the distribution during sampling. But to do that efficiently, we need to estimate a mass matrix, right, which basically you can think of as saying what the scale of the parameters are, and if you do it in a dense form, what the correlation of the parameters are. Right? And then we do adaptation, and these things are both estimated along with the step size during warm-up. Yeah?
Using your autodiff framework, are you able to estimate curvature, second order?
Yes. Yes, we are. We have it for everything but our probability densities now, but that is also, you'll hear more about it this afternoon in the coming soon features. So right now we're doing it in a fairly crude way. We have something like LBFGS, which is doing it during optimization, but we're actually rolling something out so we'll be able to do real Riemann manifold HMC, just to give away a bit of this afternoon's talk. But the really clever thing that Matt came up with for Hamiltonian Monte Carlo, and HMC is very, very sensitive to these tuning parameters. So you want to be careful with people telling you, my algorithm runs really fast once I figured out what the tuning parameters were. Figuring out what the tuning parameters are is a large part of the work, and we're doing that now fully automatically. During sampling, right, as opposed to during the warm-up phase, what's going to happen here is we adapt the number of steps, basically the time that we simulate this Hamiltonian for. This is done with a very clever algorithm based on the geometry of the posterior that tries to walk until it starts to make a U-turn. Now, it's very complicated to make that observed detail balance to make sure that the posteriors are really being sampled from the right density, but it all works. The posterior inference that we can do is we can use the generated quantities in the model to do predictions, make decisions, do Bayesian decision theory-based decisions, calculate event probabilities. We have extractors for these samples to do something very general. And then there's a popular package for Bayesian analysis in R called CODA, and we do a posterior CODA-like posterior summary, which I showed you an example of. And we like to do model comparison either using cross-validation if things are efficient enough, or using wake, which is an information criterion that asymptotically simulates cross-validation using just the in-sample data that you've got. We also do penalized maximum likelihood estimates, which I think is more similar to what everybody else was talking about earlier. You throw up some kind of likelihood function, you maximize that subject to some regularization criteria, basically shrinkage typically. And we do posterior mode finding, which will find either a map estimate, a maximum a posteriori, or a posterior mode, or it'll find a pure maximum likelihood estimate, depending on how you want to think about this philosophically. It does the same thing computationally. And we use LBFGS for this. So this also uses the model gradient, and it efficiently approximates the Hessian as it's going along. We have to disable the Jacobians on the transform, which are necessary for MCMC. Every time we transform a variable, we have to take into account the nonlinearity of that transform and the curvature of the variable transform, say going from -infinity to infinity down to 0 and 1. I do a sigmoid function. That sigmoid function isn't linear, has a different curvature. I have to adjust for that curvature when I'm doing sampling, but you don't want to do that when you're doing maximum likelihood. It's not really quite a proper probabilistic technique based on expectations, so instead we have to disable the Jacobians, which is allowed. And what we're doing right now is we're using the Hessian to estimate the posterior covariance, which everybody wants. If you're doing something like hypothesis testing, you need to get the posterior covariance out. Right now we're using curvature to estimate that based on finite differences, but we're about to roll out a more general tool for doing that. And then one of the things that people have been using STAN for, rather than just fitting models, is people have been using STAN for a research tool, and it can be used to explore algorithms. So one of the nice features of STAN is that it takes a model defined with constrained parameters like simplexes or covariance matrices, which have these really complicated positive definiteness constraints, and they transform to unconstrained support on RK. On Rn, sorry, and basically that means you don't have to deal with boundaries in your random walk algorithms and your optimization algorithms. Then once a model's compiled, you get the log probability, gradient, and Hessian out as features. We deal with data I/O and parameter initialization, which can be tricky, mapping between the constrained and unconstrained spaces. So we wrap that all up with simple wrappers with access to variable names and dimensionalities and the transforms. And in the very near future, we're going to be doing second order, higher order derivatives, and really third order derivatives as well. So that was actually where I was going to stop this morning and take questions.
You didn't mention it, but can you do things like Bayesian and parametrics, like Dirichlet processes?
No. We can do Gaussian processes if that's your non-parametric of choice, but we have a fixed number of parameters, so we can't do. Now, in most applied problems, you can do something like a Dirichlet process by approximating it with a big finite thing, but we can't technically actually jump in the Dirichlet process space. And I should qualify this, there are no discrete parameters at all. If you want to use a discrete parameter in STAN, you have to marginalize it out of the model, which winds up being clunky for users but very efficient for sampling because of the Rao-Blackwell theorem. It's much easier to sample when you marginalize things out, but harder to formulate the models.
There's kind of a big conceptual difference between STAN and the other projects. I think for the other projects, at least conceptually, it's relatively easy to imagine combining at least the algorithms
Mhm.
and possibly even the code bases to some extent, right? But maybe I don't understand the details of Stan well enough. Can you see how you would? So, for example, in VW, there's a good online learning algorithm, right?
Mhm.
Do you have a sense of how you could take advantage of that, or how that could fit into Stan, or is it just like completely different and they don't fit together?
I think you're foreshadowing the talk you had us think about for later. We can incorporate other methods, and we can, assuming they have open enough licenses, we can incorporate other people's code as well. But we haven't set this up to be extensible, to be like something that lets you just plug arbitrary pieces together. And part of the problem there is everything's going through our language, right? So, for instance, one of the things we need to add is sparse matrix representations, which we don't have now. There's lots of libraries, but it's really quite a pain to do because it needs to be threaded through, not in the threading sense, but it needs to be sort of woven through all of the language to allow expressions for sparse matrices and so forth.
Just to build on the last two questions, is there any plan, maybe to start with this afternoon, to incorporate some more of the variational stuff that's been going on?
Yes, that's one of my slides for this afternoon.
The question, thank you.
In fact, you want to talk to Alp, who's sitting right back there, wearing a name tag that says visitor.
Can you repeat the question for them?
Oh yes, do we have plans to incorporate variational inference? And the answer is yes. We're working on that with Dave Bly and with Alp. Yeah, since you got your hand up, Dave.
I was going to say, just following up on what John mentioned, it seems to me like Stan, one way you can plug it into other algorithms is Stan is an amazing tool for taking a model, compiling it into a box that gives you an objective and a derivative, and then any algorithm you have that requires an objective and a derivative, you have an efficient implementation of some kind of domain-specific, complex, constrained probability model. And I feel like Stan plus some machine learning tools would be a very powerful combination for letting domain experts express themselves in Stan and machine learning experts do what they need to do to optimize the objective function that pops out.
This may not be only to you. I've noticed a lot of the libraries that have come up have re-implemented basic statistical functions, and I'm wondering, things like LAPACK, they took years to get right. When somebody's using a newly hashed library with like 3 years in it, and the authors are claiming numerical stability and such, how, as a developer, how do you decide when to go with something that's been used for a long time versus rolling your own? What are the factors? And B, how do you assure people of something as subtle as numerical stability on A10 or something?
To answer the former question, when do we go with something else? When it exists. So for instance, we went with Eigen because it had a nice templated matrix library, so we could plug our autodiff right through Eigen, no problem. The problem is auto-differentiating an iterative algorithm like inverse or something is very inefficient. So we needed to actually implement something. When we wanted more efficiency, we had to extend that and actually do something more efficient for matrix derivatives. So we're still using Eigen to compute the basic inverse operations, right? And we inherit whatever stability Eigen has, which is improving over time. But then we also have to sort of paste on our own thing for doing matrix derivatives. The problem was with particularly the density functions and almost all of the other functions, there was no sufficiently templated version. So if you look at something like Boost, which has most of the, well, not any of the multivariate stuff, but at least most of the univariate densities implemented, it didn't allow us to template separately on each argument, which is really critical for autodiff efficiency. I think to answer the question about how can people verify that things work, well, I mean, we have the C++ code. We have pretty extensive unit testing for both the gradients and for the particular values. And we encourage people to test things themselves, right? So you can call these functions separately. You can test them. If you know C++, you can go test them yourselves. For most of our users, they can just see it in the fact that their models don't crash anymore. So the previous generation of these systems, like Bugs and JAGs, had all kinds of problems on boundaries. You do something like you multiply two things together, and then just due to the vagaries of floating point not being quite associative, you wind up with things that should sum to less than 1 being 1.0001, then you throw them into inverse logit, it crashes, right? That doesn't happen in Stan, and at least when it does, in cases we don't know about, we tend to fix it. But otherwise, I think you've got to go kick the tires yourself to really convince yourself that, you can look at our unit testing or you can try it yourself.
So
Yep.
this is super interesting for other projects, right? In particular, the autodiff and the distribution representation in C.
Mhm.
Is it technically possible to expose this in the form of a library without having to go through the Stan language?
Yes, yeah, it is all exposed in its own library. So it's fairly modular C++. So we try to minimize the dependencies among our namespaces and packages in C++ so you can pull these things out. You can't really pull any of the multivariate stuff out without also grabbing eigen, because we use that for our data structures. But otherwise, you can independently pull out just our autodiff system and just the basic C++ functions, and then you can optionally throw the matrix library and the probability density library on top of that.
Do you have any plans in kind of releasing this as a sub-project that you can use independently of Stan? Say you don't want to do Bayesian modeling, you want to do something else, but you want to have an autodiff library.
Yeah, we would like to wrap this up. First, we need to create developer-facing doc that's more than just us chatting on our own little mailing lists and during our meetings, so that it's a little easier for people to figure out how to use that. Right now, we tell people to go look at our unit tests, go look at a few simple examples that we have, and figure it out from there. Then we could wrap up separate releases. We could pull basically the autodiff is most of what Stan is. If you actually look at what the implementation is, so if you download all of Stan, you have to throw away the parser and you have to throw away some of the MCMC stuff, but that leaves 95% of the code as the numerical library underneath. So if you think you'll save a lot of space, that's not going to happen. But it would be nice to release it cleanly as a separate library.
I mean, you could combine it with tools
I
like...
think we should probably stop because people will be late for the next session. So
Okay.
let's
Thanks.
thank the speaker.